All right, recording is rolling. So welcome to Wednesday, April 26th. We're going to finish this statistics part C, the stats packet. So we're going to do part C. Okay. And then I'm going to have you guys start a quantum mechanics journal. I'll give you guys some paper later. I'm going to pass around a stapler. And so hang tight for that. I haven't given you guys this quarter page yet, although this has been on Google Classroom for a few days. If you wanted to access it there, but I'll give you guys that quarter page, and that's going to be today. All right. So let me back up a little bit, give you guys a little bit of a review, because I know there was a substitute yesterday, so it's been a couple days since you guys seen this. So the last main topic that we're studying for this class is going to be quantum mechanics. After that, we'll do the final exam review, and then I got some other fun projects, whatnot lined up. Right? But quantum mechanics requires a different type thinking than you've used all through this year up to last week. So instead of things being formulaic, you just plug things into a formula and say, okay, here's exactly where the ball lands. Here's exactly what the energy change. Right? Instead, you have to think statistically, like probabilistically. So where exactly will a particular atom be? Well, that's really a matter of probability than anything you can say definitively. Right, so I want to lay the groundwork for that so you can think in terms of probabilities and statistics. Right? Now, some of you guys have had stats classes or in a stats class, so this is either a good review for that, right, or right, can reinforce those ideas. Right? But if you haven't, then some of this stuff might be new. So the other day we were looking at distributions of heights for different populations. We were looking at like dogs, people, and trees. Right? And we were looking at two main properties, like what is the mean, like the average, so you add them all up and divide by the number there, which is something that you guys have known at just like elementary school and imagine, right? But also we were looking at this idea of like how spread out is the data. That's called standard deviation. We went through the whole process for that, as you guys have the calculator. Like dogs, for example, how their heights are way spread out. Oh, thank you. People are kind of in the middle, and I picked some trees. Maybe they're all like selected to be Christmas trees that are all kind of the same heightish, so there was almost no variation at all. Right? Okay. And then here's the way you can calculate that. We went in another step and calculated something called z-score. So a z-score could be for a particular individual. Where do you sort of land within your population? So if you had a height of 6'2", I say, well, okay, well, I'm taller than average, but is that just a little bit taller than average? Is that crazy taller than average? Right, so you can, if you know the average height within your population and you know the standard deviation, you can put that all together with your particular height and you can calculate a z-score. Right? And then you can go to this table here and it'll tell you how tall you really are compared to everyone in the population. So, oh, yes, I'm taller than like 70% of people or something like that. Right? Right, so we did all that. Right. We're also looking at, like liquid within bottles. So that's another example. Anything that's normally distributed. Height isn't exactly normally distributed, but I'm just using that sort of as an example because I think it's a pretty tangible example, right? But hey, if there's a factory like filling up bottles with water, I bet there's some kind of normal distribution associated with that, right? Probably pretty small standard deviation, but you guys got later, right? Okay. All right. And now we're on the stats page C. Right. Now, every one of these pages introduces some new idea. Right. So here, what's new here? Well, what's the same? Right. Here's how to calculate the mean. Right. Add them all up, divide by the number there. Here's standard deviation. How spread out is the data. Here's z-score for, say, an individual. Right. So remember, this is the number of standard deviations you are from the mean. And then you can refer to that z table and figure out something about where you land among the population percentage-wise. Okay? But here's the new idea: is we're going to start to put individuals into groups. Right? We're going to start to group them together. Okay? And this is going to be the bridge to like particle physics. Is one application of this. Okay? So we'll run through two examples. I've got a height example and a filling up bottles with liquid example. Okay? So number one, right, so everybody good so far? Any questions so far? Right, that was all a quick review from a couple days back. Everybody good? Right, so question number one, suppose that the average human height is, right, now remember, my numbers are different than your numbers, but mine says 177 centimeters. Let me write that so it's bigger for the video. Okay? And the standard deviation of 9.0 centimeters, right? So I've got the average, and then standard deviation. Remember, think of this sort of like a plus or minus factor. So this average plus or minus the standard deviation should cover like 68% of the population. Right? Remember that your numbers are different than mine, but okay. So first question, what is the expected value of height of the next person who walks in through the door? I mean, let's make it completely random. It could be any of 7 billion people, right? Just for argument's sake. shouldn't it just be the average? Can you guys just copy paste that number right there? Just copy paste that number. Right? Now, don't copy what I have because my numbers are different than yours, but you guys get the idea, right? And what is the standard deviation of the next person walks in the door? Oh, well, shouldn't that just be this number copy pasted right here? You know, just copy paste that right there. Okay. Okay. Are we good so far? Okay. Next question. Therefore, what is the percentage chance that the next person who walks in the through the door has a height greater than or equal to, say like 185 centimeters, for example? Write that a little bit bigger for the video. 185 centimeters is this number right here. Now that's getting pretty tall. Well, I know it would have to be less than 50% because that's pretty tall, but how exactly? So we're going to do this in two parts. First, we need a z-score. So z, remember, take your sample, so that individual, subtract the mean, and then divide by the standard deviation. So in my case, the target value is 185 centimeters. The mean is 177 centimeters. Right? So there's the difference. But remember, I'm trying to get a count of the number of standard deviations. So if I divide by the standard deviation, which is this many centimeters, that'll tell me a count of the number of standard deviations above the mean, which is going to be, that's what z-score is. So that times that, all in the parentheses, divided by that, right? And I'm getting this number right here. If you did this correctly, you should get something between -3 and 3. Right? Right. Did everybody get something between -3 and 3? Okay. Right. Who has a question? Right. You guys good? Right. Awesome. Right. All right. So how about this probability? You guys ready to shop that z table? Right. So you have your z-score. You have your z-score. Okay. So mine's 0.89. So flip over here. Actually, I think everybody made everybody's z-score come out to positive for this one. Okay. So since mine's 0.89, scroll down to here's z, here's 0.8, right? And then I can go across the table, 0.80, 0.81, 0.82, 0.83, right? And now since mine's 0.89, I need to scroll all the way to the right to 0.89. Okay? Now, make sure you guys are following. Is anybody not able to find their place on the table? Great. Now, the number on my table says 0.81. That's like 81%. Okay? You guys get like 81%? Okay. Now, your numbers are different than mine, but mine says, now the fact that mine says 81%, hey, that's how many people I'm taller than, or the next person that walks in the door. The next person that walks in the door, if they were 185 centimeters, they would be taller than 81% of all people. Okay, see that? But the question isn't that. The question is, how large is this tail to the right? Like, what was the percent chance that they would be that tall or taller? So, can I take 100% of all people, subtract the 81% that they're taller than? I think I've been saying 81%, right? Yeah, 0.8133. That's like 81%. I'm rounding a little bit, but 81%. So that'd be 19%, right? Wouldn't that be true? So if the next person that walks into the door is 185 centimeters tall, I can say they're taller than 81% of people, but they're also shorter than 19% of people, right? And that is the answer to this next question. 19%. Okay. So whatever number you have here, again, everybody's numbers are different, but I think I made it come out so that it's less than 50%. Right. Who has a question? Who has a question? And so everybody do good? All right, nice. All right. Okay. What's your z-score? Got one? Okay. If your z-score is 1.0, here's 1.00 is right here. It's 84%. If you're taller than 84% of people, how many people are you shorter than? How about 16%, right? 100% minus 84% is 16%. So you got 16% right here. Did you get exactly 1.00 for your z-score? Then that's the first column, 1.00, okay, which is like 84%. Okay. All right. So that's a good question there. Any other good questions? So everybody's got these boxes filled. Right. Now, actually, everything we've done up to this point is just a review of stuff that we already did on Monday. Right. Are you guys ready for the new stuff? Hey, here's the new stuff. Now we're going to start putting people in groups. Right? Use the same average height as in number one. What is the expected average height for a group of 5 people that walk in through the door? Right? Well, do you guys think the average is still the same? Can you guys just copy paste the exact same average? Right? So we're going to have a group of 5 people walk in the door. Why would we have that? I'm about to give you guys a story. Right? Now, what's the standard deviation for 5 people? Do you guys see this new formula right here that says standard deviation for a group is what it is for an individual divided by the square root of the group size? So the standard deviation for 5 people is what it is for 1 person, which for me was 9 centimeters. That's like, think of that plus or minus factor, divided by the square root of 5. Because now I'm putting on the 2 group of 5 people. 9 divided by the root 5. Right? And well, I'll call that 4.0. And that'll be a centimeters. Okay. Okay. Did you guys also take your standard deviation, divide by the square root of 5? And now you have a new standard deviation. Right? Everybody got that? Right. Now, what's that about? I'm about to give you guys a story. Okay. So suppose we're aliens up in a spacecraft and we're hovering around Earth and we're looking down on Earth. And we're trying to figure out something about human civilization. And we can't see a lot about people. We see people all walking around. We can see what their heights are. We can get that. We know how to get that. Right? But we see a bunch of people like walking into these arenas that have like roofs. So we can't see what's going on inside these arenas, but we know it's a bunch of people walking into these buildings. We're trying to figure this out. What the heck is going on inside that arena? And I come up with a hypothesis. I say, hey, you know what? I think I know what's going on. Based on all this data, I have a hypothesis that there's such a thing. I think there's such a thing as a game called basketball. And I think this is how it works. I think that there's like, probably have to take this ball, you have to put it in this hoop, there's some elevation above the floor. And so, and I think it's like teams of 5 people. And so given the rules of this game, based on all this evidence I've seen, I think it would be advantageous to be tall. In fact, if there were groups of really tall people walking around, like groups of 5 people that were really tall walking around, that would be pretty strong evidence that this game basketball exists, right? That's my hypothesis as I'm sitting up here hovering in my spacecraft, right? You guys kind of get that, right? So if we saw groups of 5 people, right, like what's sort of the chance that they would all be really tall, just completely randomly? Because you wouldn't really expect that to be like randomly the case. But if basketball exists, which in my hypothesis it does, then now you would expect to see congregations of 5 people that are all really tall, right? Right? Does that make sense? Right? Now, here, okay, so let's run the numbers here. So therefore, what is the percent chance that the average of the next 5 people that walk through the door are all collectively on average super tall, this 185 centimeters? Okay? So now we're going to find z-score for 5 people. Right? Now we've got them all grouped together. Okay? So I'm going to take the target value of 185 centimeters, same as it was before. I'm going to subtract the average of 177 centimeters, same as it was before. So far the numerator looks the same. Okay? Divide by. But now the fact that I've got them grouped together, I've got this new standard deviation. Right? You guys get that? So let's see what this is. Yeah. Okay. And here's my new standard deviation. Or sorry, my new z-score, I should say, right? Divide by the new standard deviation, you get the new z-score. That number goes right here. Right? Everybody should have their new z-score. Who does not have the new z-score? Okay, awesome. Everybody has the new z-score. Okay. Now, remember how the z-score is usually somewhere between like -3 and 3 is a pretty common thing? Okay. Well, my old z-score was a little bit less than 1. Okay, so above average, but not crazy above average. But now z-score 2, that's getting pretty far out there. Let's see what the percentages look like. Let's flip to the z table. Okay. That should work for you too. Your z-score should have just gone up because your standard deviation went down. Z-score of 2.00, that's like right here. I'm looking at 97.7%. Okay. Now, remember, that's taller than 97.7% of people. So how many people then therefore would be taller than that particular group? 100% minus 97.7% is like 2.3%. And that's the number that goes right here. Okay? So if you're following the story, right, for one particular super tall person, I'm going to define this height as like super tall, right, to walk through the door. Okay, that's going to happen every once in a while. I mean, there are tall people in the world. Maybe there's a 19% chance the next person walks through the door is going to be super tall. Okay. But what's the chance that a collective group of 5 people are all going to collectively be super tall? Well, no, that's going to drop way down to closer to 2%. Right. Now, again, your numbers are different than mine, but you should have seen a drop off like that. Do you guys get a drop off like that? Went way down, maybe like single digits. That worked out? Worked out for you guys? Right? Right. So that wouldn't be something that you would expect to see normally or just randomly. Right? You could call it so like a null hypothesis type scenario, right? So if you did see groups of 5 people walking around and they were all super tall, do you guys see how that would be evidence that, yeah, there probably is a game exists that's called basketball that has the rules that would it'd be advantageous to be, right? You guys see that? Right? So that would be evidence that basketball exists, right? Now replace basketball with the Higgs boson, and now you have particle physics. Okay? Guys get that? Okay. All right. All right. Let's do one more example because I know that was good. It's good to reinforce the idea, right? So we'll do this again, except now let's switch over and look at like filling up bottles. Okay? So suppose the average volume of water in a certain brand is, okay, now mine says 1,000 milliliters with a standard deviation of 4 millimeters. So what's the expected value of a single bottle of water chosen at random? Can you guys just copy paste that average value? Right? Just pull a single bottle off the shelf. How much liquid is in it? I don't know. I guess I'll guess the average, right? That's probably the best guess, right? And what's the z-score for a bottle with 1,005 milliliters? Okay, so now I pull another bottle off the shelf and it looks like it's a little bit overfilled. Or is it a little bit overfilled or is it a lot overfilled? Well, we're gonna find out. So just running out of ink there. So I'm looking at a target value of 1,005 milliliters. I know the average for lots of bottles is an even 1,000. Okay? And there's this standard deviation, like a plus or minus factor of like 4 milliliters. Right? Let's see what the z-score is for this particular bottle. Like 1.25. 1.25. Right. Again, I tried to make the numbers come out somewhere between like -3 and 3 about. Okay. Did you guys get something between -3 and 3? Right. Probably between 0 and 3. I think I mean. Okay. Everybody got their z-score? Everybody good? Okay. Who's got a question so far? Who's got a question? All right. Everybody doing good. Therefore, what is the chance that the next bottle of water chosen has a volume greater than that? Ooh, it's z-table time. You guys ready for the z-table? Okay. So I know my z value is 1.25. So let's go. 1.2 here, 1.20, 1.21, 1.22, 1.23, 1.24, 1.25. I'm going to round this to the nearest percent. I'll call that 89%. Okay, 89. Now, remember, guys, that's 89% is less than that. So if 89% is less than that, what's the chance that a bottle would have greater than that? Is that like 11%? Right? Wouldn't that be the case? Right? So that goes right here, 11%. Right? So if 89% of bottles have less than this, that means the other 11 would have greater. Okay? You guys good? Okay. Okay. Again, that's stuff that we did back on Monday, right? So, but now we're going to start putting bottles in groups, right? And here's why. Maybe I'm sitting here, I'm starting to pull bottles off shelves and saying, hold on a minute. Our machines back in the factory, we got like, let's say we got 10 different machines. And I have a suspicion that one of our machines is consistently overfilling these bottles. Maybe only by a little bit, but I think it's off. Right? I think it's like not aligned correctly. I think it's consistently overfilling these bottles. Right? And I'm talking with my coworkers back at the factory, and they say, no, all the machines are doing the same thing. And I say, no, I really think this machine is like overfilling these bottles consistently. Say, okay, well, prove it. I say, okay, well, let's pull some bottles. I'm going to pull 5 bottles from that machine that I suspect, and we're going to see. So use the same average volume and standard deviation. What is the expected average volume of a group of bottle per 5 bottles? Okay, well, null hypothesis, I should expect. I mean, if if my coworkers are right that all the machines are the same, then we should expect 1,000 milliliters. That's the expectation, right? So no, they're all 1,000, right? I don't think so. We're gonna find out. Right? That's our null hypothesis. So what's the standard deviation for a group of 5 bottles? Well, I know for one bottle it was like 4 milliliters, but now I'm gonna group it in 5, so I'm gonna divide by the square root of 5. Can you guys take your regular standard deviation and divide by the square root of 5? Because 5 bottles. Right. What is the standard deviation of 4 milliliters divided by the square root of 5? And that's 1.79 milliliters. Got 1,000 milliliters here. Got 4 milliliters here. Okay. Okay. Do you guys get a standard deviation for a group? Okay. Now, what's the z-score for a group of 5 to, on average, all collectively have a volume of 1,005 milliliters, right? Because if I pull 5 bottles and the average is like way above average, now that's more evidence towards my position, my case, that I think some machine's overfilling. So now let's do a Z for 5 bottles. Right. So we got 1,005 milliliters on average for all 5, compared to the expected average of 1,000 milliliters. Right. And remember, z-scores accounted the number of standard deviations. The new standard deviation for a group of 5 is like 1.79 milliliters. This number here. Okay, you guys following? That working for you guys too? Who's got questions so far? Questions so far? Okay. Remember, before I would divide by 4. Now I'm dividing by a smaller number, which is going to give me a larger z value. Okay. I'm getting a z value of 2.79. 2.79. Woo! Right. That's getting up there, right? Because that table only goes to like z of 3.5, so this is getting pretty high, right? 2.79, right? Right. Everybody good? Okay. All right, now let's check out the z table. 2.7, scroll to the right, 9. Okay, now this says 99.7%, but remember, that's everything that would be less than that. Guys, if everything less than that is 99.7%, then 0.3%, there you go. Take 100%, subtract 99.7%, that's going to be a 0.3% would be like that volume or greater collectively for a group of 5. Okay? So 0.3%. That's less than 1%, right? So I go back to my coworkers and I'm like, okay, if you guys are right, then that's really unlikely because there's only like a 0.3% chance that you guys are right, right? There's like a 99.something% chance that I'm right, that this machine is in fact overfilling these bottles consistently, and I can say that based on these 5 bottles. Okay, right, you guys got that? Okay. Now replace bottles with tau muon, and you got particle physics. Okay, right, because over at Large Hadron Collider, what they're doing is they're colliding these particles together. They're looking for certain properties of collisions, and now these collisions are always really messy, but they have like thousands, millions, billions of collisions. They can aggregate all the data. They can do statistical crunching kind of like this. And they say, okay, if the Higgs boson exists, if the tau muon exists, if the lepton exists, then we should expect in the aggregate these numbers to pan out this way. Okay, you guys got that? Right, any questions on stats pages? All right, any questions? All right, so here's what, you can check your numbers. If you feel good about your whole stats packet, then turn that into the grade tray. I know a couple of you guys weren't here on Monday, so you can catch everything we did on Google Classroom. You guys know I post all these videos to Google Classroom, and you can just turn this in sometime later this week. It's fine, right? And then I'll give you guys points for that. All right, so we're about to switch gears here. I'm going to give you guys this quarter page with a bunch of quantum mechanics topics. I'm about to give you guys a bunch of paper, and I'll tell you guys what's going on next. Actually, let me go ahead and pause the video at this point because we're going to transition here.